On page 73, we're going to look at calculating some areas, and I'm going to use the formulas that I'm used to. You can use the formulas that you're used to. We should get the same answer as long as we're calculating correctly. So starting with number 1, it says to find the area of the figures. Remember to label your answer in square units. So here we have a square. And the formula that I've used for many, many years now is side to the second power. You can also do length times width. But one of these sides is 4, and 4 to the second power is 4 times 4. And so that's going to be 16 square inches. And I'll write it out this time, and I'll show you the abbreviation that I usually use. You can also write it as 16 inches square. So the answer to this question is 16 square inches. Number 2 is a rectangle. So the formula that I want is length times width. In my mind, length is always the longer of the two sides, but it really doesn't matter because you're building up. So area is 5.3 times 3.4, and they did not tell us to round, so I won't. This one is in square centimeters, or you can write out square centimeters. Number 3. Again, we're dealing with a rectangle, so we have length times width. And this time, both sides are in inches. You would always want to make sure that your units match. I do that subconsciously. I've done it for so long. But what I'm talking about is this, that if this one is in inches, so is this one. You need to have like units before you start these problems. Number 4, this is a parallelogram. It's a rectangle that's leaning. And we do have miles and miles. That's good. Area of a parallelogram is base times height. So the base is 8 and the height is 6.9. You are multiplying those two together. And again, it does not say to round, so I won't. And this is 55.2 square miles. And here we have another parallelogram. They're showing me the height of this thing as a vertical line. You always want to look for height at a 90-degree angle. So this is your dashed lines mean the line is not really there. It's an imaginary line or a theory line. But this is going to be the height of this parallelogram. So the area is base times height. And the base is 0.7. The height is 0.6. And so when you multiply those two together, you will get 0.42 square centimeters. And number 6 is a square, true square, so we can use s to the second. One side is 3.7. Remember, that doesn't mean 3.7 times 2. It means 3.7 times 3.7 times itself. So the area here is 13.69, and I'm using a calculator. I should have told you that. No way I could do that in my head. I have a background in forensic science, and this would be a good example. If a person has escaped from prison or from some fixed location, you will usually set up a perimeter of about a 4-mile radius. Now that would be a circle, but you're looking at the ground that could be covered in any direction. That's a good application of area when your distance is this large. Miles is huge. Another one would be the Bermuda Triangle. where you would calculate the number of square miles or square kilometers in the Bermuda Triangle. So they're trying to give us different examples here. Some of them are very large dimensions. Use the diagram of a regulation tennis court for problems 7 through 10. So let's take a moment to become acquainted with this diagram. And the first thing my brain does, just from pure habit, is to look for those units to make sure they're not trying to trip me up, that everything is in feet. And indeed it is. So we have some dimensions here. I also noticed that there are two different types of courts, or not types of courts, but types of baselines. There's the singles dimension and then the doubles dimension. So the doubles baseline would be this blue one. It's wider because there are two people playing. And then the singles baseline is not as wide. So we'll have to pay very close attention to what we're being asked to find. Also, I see that the regulation sideline for both is 78 feet. So let's take a look at the first question. A singles court, so we're looking at this dimension, will be painted a contrasting color. How many square feet, will be painted? So the singles court is going to be this blue one. So if you want to play a game of tennis and you are playing against another single person, you're limited by this blue area. It would be against the rules to go into the white sidelines. So we want to know the area of the blue. What is the area in total of this blue court? So the first thing I'm going to do is draw. I can erase, so I'm going to draw up here. We have one rectangle that is 18 by 27. So I'm going to use the longer one here. And let's do a little bit of math. 27 by 18. And what am I doing? I'm thinking of composites, and I'm going to erase this, but hopefully you have already seen what I did wrong. Why am I using 18 when I would just have to go ahead and do it by 21, and then 21, and then 18 again? What I want to do is this. I'm sorry, I'm tired and I just wasn't paying attention. You can do it that way. It will certainly work, but it'll be a lot of work. What if we just said of the blue area, the length is 78 feet and the width is 27. So if I multiply those two, length times width, I would get 2106 square feet. And that's my answer. Instead of having to go through all of those four parts, you can just do it once. Or you can do the four parts if you want to. On a singles court, so in the blue, what is the area of the rectangle between the service line and the baseline? So we're talking about this dimension, the one that I was getting ready to do. We're looking at the area between the service line and the baseline. So I'm just going to go ahead and do that down here. Of course, length times width is the formula. And it's 27 long by 18 wide. And when you do that multiplication, you will get 486 square feet. Again, that's on a singles court. A ball being served must land in the opposite small rectangle adjacent to the net. What is the area of space where a serve must land? So a ball being served must land in the opposite small rectangle adjacent to the net. So if I am serving somewhere in this area, it has to land in the opposite. So we're looking at across the net, adjacent to the net. So we want to know the area of that rectangle. So I'm going to do, let me go ahead and plug in some numbers here. We found that this is 486 square feet. So that means this would be 486 square feet. We want to know that little rectangle right there. So this quarter is what I'm looking for. So let's get a formula. We know it's a rectangle, so that tells us our recipe. We need to get some dimensions here and be very, very careful. Let me just erase this out and color it if I can. I want you to be able to visualize. So much to do with geometry is the ability to visualize what they're talking about. So we're going to have to do a little bit of work to figure this out. The dimensions we're given go corner to corner. We don't want to go corner to corner. We know that this dimension is going to be half of this dimension. So half of 27 is 13.5 feet. And that is this dimension. Now I need to know this one. So that one's going to be 21. It's the same width as the one right beside it. So here's the area that we need to find. 21 times 13.5. Be very careful with those measurements. You have to work for those a little bit. So 283.5 square feet is the area of that little rectangle. 283.5 square feet. Okay. And just because we're going to have to do this in the next video or one soon, let's go ahead and calculate the total area using these composites. And I'm just filling in the area. I'm not going to do the formulas for each one of these. But remember, this total area should be 2106. That's what we found in problem 1. So I'm going to get my calculator, if I can find it. And I need some light. I meant to tell you earlier, if you hear a strange noise, the cat's in here and she's snoring. She's really sawing logs. So I'm just adding up these. I'm going to do 283.5 times 4, because there are 4 of those. So 283.5 times 4. And let me write that down here. 283.5 times 4. And then I'm going to add 486 times 2 and see what we come up with. If we've done everything correctly, we should come up with 2106 to match that one right there. And we do indeed come up with that. So either way you do that problem, number 7, you will get the answer you're looking for. All right, there are 9 square feet in 1 square yard. That's a conversion. And as soon as I see it, I think of a ratio proportion problem. But we'll see. What is the area of a regulation doubles court in square yards? So the first thing we need to do is find the area of a doubles court. And the doubles court includes the blue area and the two sidelines. So we have the length of the court is still 78, but this time we're using the 36 feet right there because we're going all the way across. Doubles courts are wider. So area is 78 times 36, and that is 2808 square feet. But we don't want to know square feet, we want to know square yards. And we are given the conversion that there are 9 square feet in 1 square yard. And we are trying to convert this many square feet. So you will multiply and divide by what's not in the peanut or in the cross product. So 312 square yards is actually the answer we are looking for. So be very careful with that one. That conversion, it grabs me as I'm reading it. Makes me think of ratio and proportion. Number 11. 2 rectangles have different dimensions but the same area. Do the rectangles have the same perimeter? Explain your thinking. Draw an example to support your reasoning. And the answer here is no. If the dimensions are not the same, for example, they want me to draw an example. So let's do this one. Let's do a long, skinny rectangle that is 10 feet by 2 feet. So the area is going to be 10 times 2, that's 20 square feet. And then consider the rectangle that is something like this. That is 5 feet by 4 feet. So area is going to be 5 times 4 or 20 square feet. So let's look at the perimeter of each of these and see, just because the areas are the same does not mean the perimeters will be the same. It could happen that way, but it's not a given. So for this long skinny rectangle, we have a 10 plus a 10 plus a 2 plus a 2. So our perimeter is actually 24 linear feet. And then over here we have 5 plus 5 plus 4 plus 4. So our perimeter is only 18 linear feet. So the answer here is no. If the dimensions are not the same, the perimeter is not the same in most cases. Now, it's possible that you could have a perimeter that could come out the same, but I can't think of one just right off the top of my head. I'm sure there are some numbers somewhere in the world that would work for, but in general, no, they will not have the same perimeter because the dimensions are different. Perimeter is the distance around the outside. So the dimensions of the sides are not the same. Okay, number 12. They want us to draw. I like these problems. They make us think outside the box. No pun intended. Let me white this out and we'll use this space to do our drawing. Okay. A figure has an area of 100 square feet. Draw and label a square, a rectangle, and a parallelogram, each with an area of 100 square feet. So I'm going to start with the square because that one is the most, I won't say difficult, but it's the most limited. For this to be 100 square feet, the sides have to be 10 because 10 times 10 is 100. A rectangle's a little more flexible. You've got more possibilities for the rectangle. For example, you could do a 20-foot rectangle by a 5-foot width. So area is 20 times 5. Area is 100 square feet. A parallelogram. It's a little bit harder to draw, especially with my art skills. Now remember, the leaning side is not your height. You have to get a perpendicular height. So the height has to make a 90-degree angle with the base. And so we need the base and the height to be the dimensions we want. So I'm going to use a 25-foot by a 4-foot. And clearly that's not to scale, but 25 times 4 is 100 square feet for the area. So these examples fit the description that they gave us, and you have a lot more leeway with the rectangles and parallelograms. Square, it has to be square, has to be the same on the outside. And this will actually illustrate that perimeter thing for us. If you do perimeter of a square, it's going to be 4 times the side. So that's 4 times 10, or 40. Perimeter of a rectangle is 2 of the long sides plus 2 of the wide sides. So you have 2 of the 20s plus 2 of the 5s. So you have 40 plus 10, that's 50. And then on the parallelogram, you would have 2 of the long sides and 2 of the wide sides. And we can't solve this one because we don't know the width. Now we could use algebra and solve it because we do know perimeter is no, we don't. We know area. So this one, I don't know that dimension, so I cannot tell you the perimeter. But it would not be the same as the area, not automatically. These are some good problems. They really make us think.